Single replacement reactions are also called single displacement reactions, so you may have seen them called either name. But what they are is when you take an element, react it with a compound, producing a new compound and a new element. Now, if you're a new high school chemistry student, you are kind of being misrepresented there. What's actually happening is that there's an electron exchange occurring. So what's important for single replacement reactions is that the electrons will only move in a certain direction, from one thing to another, not in the reverse direction. And so part of single replacement reactions is whether or not the reaction will actually occur. So in conjunction with single replacement reactions, you're often provided what's called an activity series, which gives you a list of what the most reactive metals are and what the least reactive metals are, so that you can figure out whether or not that reaction will occur or not. So let's go ahead and look at a couple of examples. So let's say that I take zinc metal and a copper chloride solution. And I want to know if there's going to be a reaction. What I would do is I would look at, so in this case I have a metal, and it's going to replace the cation in an ionic compound. So I'm comparing copper and zinc. Now typically in activity series we'll start with the most reactive metal on top or on the left, and then it will move to the least reactive metal. So the fact that zinc is higher means that zinc is going to be the thing that ends up in the form where it's in the compound. So currently, I have zinc in the elemental state and copper in the compound. So these are going to trade places, and this reaction will occur. Okay? So I'll end up with zinc plus 2 charge, chloride minus 1 charge, so ZnCl2. That'll be dissolved in water because it's soluble, and I will end up with some copper metal. Balancing is really straightforward for this one. So this reaction will occur. However, if I had started with a situation where I had zinc nitrate solution, let's say, and copper metal, then I would have been in a case where my zinc is already in the compound and is higher on my list, and so therefore this would have led to no reaction taking place. Okay? So a big component of single replacement reactions is whether or not the reaction itself will actually go ahead and take place. So I did this reaction a little earlier, a couple days ago. And so this is a piece of copper metal in a zinc solution. You can actually see some of the zinc salt has precipitated because some of the water has evaporated. And then over here, I have a piece of zinc metal that's been in a copper solution. So you can note that the blue color of the copper solution is now gone. And instead I have a bunch of copper metal formed, and actually some of the zinc salt has also precipitated out in there. Let me see if I can switch the color on these and give you a little better view from up here. Just for a second. So here's our copper metal in our zinc solution, and then here is our zinc metal, and it's reacted with the copper solution to form copper metal and the zinc chloride. And so we can see that in one, no reaction has taken place, and in the other, there has been a reaction. And we end up with the same result for both, is the other thing you can kind of see, although we have some excess zinc metal in there. Okay, so let's go ahead and do some examples of these and also work on some exceptions. Let's start with exceptions. Or not exceptions, but alternative single replacement reactions. You may note that on the activity series, hydrogen is present. So right here, here's your hydrogen. So any of the metals that are above hydrogen, if you add them to an acid, you'll get a reaction. If you take copper or mercury or silver or gold and add it to an acid, the acid component of that will not react. Okay? And then in addition to that, there is another point, for my activity series up here, it's right here, where the metals above that point will actually displace hydrogen from water. So let's take a look at what those reactions look like. So metal plus an acid. So let's take aluminum metal plus hydrochloric acid. So we take a solution of hydrochloric acid and aluminum metal. There would be a reaction because we have our more reactive component higher up. And then we would see a displacement where the aluminum would displace the hydrogen. So our products in that, we're going to get hydrogen in its elemental state. Now hydrogen is one of the diatomics and would form a gas. And then I'm going to end up with aluminum bonded to the chlorine in an ionic compound. And it's going to be in water, in solution, because I have the water present. So +3 charge, -1 charge, AlCl3. And that would be aqueous. And we would end up with a 6, 3, 2, and a 2. Balance that. That would be our balanced reaction. Now, if I were to take something and say, okay, I'm going to take mercury liquid and add that to hydrochloric acid, that would be a no reaction, because mercury is below hydrogen on the activity series. And so the electronic transfer there is not going to take place. Now, if I were to go above here, now I can actually react with water to displace the hydrogen. And that reaction is a little different than the other one. The other one, you're making hydrogen gas, and then the other compound, this compound is going to work out a little differently. So let's say we take sodium plus water. Okay. And just for comparison purposes, let's do also sodium plus hydrochloric acid. So sodium plus hydrochloric acid, we would make hydrogen gas and sodium chloride NaCl. And let's assume that everything in here is aqueous. Balance 2 and 1. So the sodium displaced the hydrogen. However, when the sodium displaces the hydrogen from water, you will make hydrogen gas, but you will retain a hydroxide, not just the oxide. So you'll end up making NaOH. Also aqueous, and you would end up with 2, 2, 2. Okay. So that's a little bit different here. We're not just ending up with any sodium oxide. It could be through the reaction with the water, or it just could be the natural product. So lithium, potassium, sodium, and then a couple of the second column, calcium, barium, strontium, those will react with water. And then in addition to that, we also have halogens. So halogens, if we have chlorine gas, and we react that with sodium bromide solution, the halogen reactivity series is literally what's on the periodic table. So as you move down the periodic table, it becomes less reactive. And at the top will be the most reactive. So fluorine will react with anything. It's hard to store fluorine. Chlorine will be very reactive. It will react with anything except for fluoride. So whichever one is more reactive will end up into the compound form. And so chlorine being more reactive than bromide here, what we're going to see this turn into is this is going to turn into sodium chloride. And then we're going to produce bromine as an element, which is diatomic. Okay, the balance we would put 2 and 2. Okay. If, on the other hand, we're to flip things around and say, okay, I'm going to add iodine solid to sodium chloride solution, then I would be in a situation where the iodine would not be able to displace the chloride, and we would end up with no reaction. Okay. So single replacement reactions, you're going to see an element plus a compound. There are various ways that can occur. It can be a metal plus an ionic compound. It can be a non-metal plus an ionic compound. It can be a metal plus an acid, or it can be a metal plus water, where if it's the alkali or alkaline metals, then that might be a reaction. And then we're going to see our salts, ionic compounds are traditionally going to be in the aqueous form, so we can actually get the reaction to take place. They don't have to be, but usually they are. And then our elements, we're going to be able to figure out what state of matter they are. So that would be single replacement reactions.